Hey everybody, welcome to week 9. This is the final week in our series. Today we're going to be talking about public keys and we're going to be talking about more of a theoretical cryptography. So let's get started. So for our session this week, we're going to be talking about a couple different objectives here. We're going to be talking about public keys encryptions. We'll dive back more into digital signatures. Then we'll talk about some ethics of public keys, some legal aspects. We'll dive into more of theoretical stuff like quantum computing and public key cryptography. And then we're going to end this session just talking about this big phenomenon of Bitcoin and how it relates to cryptography. So let's get started with the introduction to public key encryption. So, public key encryption is a cryptographic system that involves two keys. This type of encryption is a cornerstone of modern secure communication, and it is used across a wide variety of applications, from secure emails to secure web browsing and even secure remote access to systems. Unlike symmetric encryption, which uses a single key for encryption and decryption, public key encryption uses a pair of keys. These are mathematically related but not identical, which is why this system is called asymmetric encryption. The different roles of these keys allows for secure communication without the need of a secure initial without a secure initial exchange of a shared secret key. And a public key encryption system, the public key is available to everyone and it is used for encrypting messages or verifying signatures. The private key, however, must remain secret and is used by the owner to decrypt messages or create digital signatures. It is crucial to understand that while the keys are related, you can't feasibly calculate the private key from the public key. This is what provides the security in a public key system. The major benefit of a public key encryption is that it allows parties that have not previously met to communicate securely. The public key can be distributed openly, and the private key, which remains confidential, can be used to decrypt any message and encrypt it with the public key. Additionally, a public key encryption provides a method for provides a method for a digital signature, as we'll talk about later on, which are an important tool for verifying the authenticity and integrity of data. The usage of public keys encryptions are diverse and widespread. In the realm of digital communication, it is used for secure emails. Encrypted messaging apps like WhatsApp and other secure web browsing via SSL TLS protocols. It is also the basis for creating and verifying digital signatures and essential to aspects of modern digital security. So next we're going to talk about how it works in depth. So, a digital signature is a mathematical scheme that is used for verifying the authenticity and the integrity of a digital message for message or a document. It is a electronic stamp of authenticity. And in essence, digital signature provides a set of secure capacities such as authenticity, authorization, integrity, and non-repudiation. Digital signatures are created using the sender's private key and can be verified by anyone with access to the sender's public key. This is an application of asymmetric cryptography, where a pair of keys, one public, one private, is used for encrypting and decrypting. Now, let's actually talk about how this process works. So, first, in step one, we will have to create a hash of a message. So, when creating a digital signature, the first step is to convert the original message into a hash. This is done by using a cryptographic hash function, such as the SHA 256. A hash function takes an input, or a message in this case, and returns a fixed size string of bits. The output, the hash, is unique to each unique input. Even a small change in the message will produce a significant different hash. Next, we get into step two, encrypting the hash. Once the hash is created, it's then encrypted with the sender's private key. This is done using an encryption algorithm like the SRA, DSA, or the ECDSA. SA. The encrypted hash is the digital signature. The original message and its digital signatures are then sent to the recipient. Step 3, decrypting the digital signature. Upon receiving the message and the digital signature, the recipient then decrypts the digital signature using the sender's public key. Remember that in public key cryptography, anything is encrypted with a private key and can be decrypted with its corresponding public key. Next, we'll go into step 4, creating a hash for the received message. The recipient runs the same hash function on the received message to create a new hash. And then lastly, we compare the hashes. The hash obtained from the decrypting, so the hash obtained from decrypting the digital signature or the original hash and the newly computed hash are compared. If they match, it means that the integrity of the message is preserved, which means that the message was not altered during transit, and that the message is authenticated. The message, which means that the message is indeed from the claim sender. If they don't match, it indicates that the message was tampered with, and it's tampered with, or the sender is not authentic. Okay, next we'll go into the practical uses for digital signatures. So there's different ways that it is used, and we'll talk about these different areas. These are just points that I wanted to point out. These are not all, so these are not limited to this, but we'll claim some of these right now. So when we talk about document signing, a digital signature authenticates and verifies the integrity of the digital documents, assuring that the recipient that the document is indeed the original from the claim sender and hasn't been tampered with. For an example, a legal document like a contract and a proposal can be digitally signed. Governments often digitally sign official documents to verify their origin and the integrity of the data. Next, we'll talk about signing. So, software developers sign their programs with a digital signature to ensure users that the software indeed originated from them and has not been modified by a third party. For instance, when you download an app from the Apple App Store, Apple uses a code signing to ensure that apps haven't been tampered with and truly comes from the claimed developer. Next, we'll talk about email signings. By signing emails with a digital signature, the recipient can verify the sender's identity and the email's integrity. For example, using protocols like the Pretty Good Privacy (PGP) or the Secure Multi-Purpose Internet Mail Extension S-MIME, you can digitally sign your email to provide these assurances. Next, we'll talk about the SSL certifications. Websites uses SSL or the secure socket layer or the TLS, this transport layer security certifications to establish secure communication with secure connections with users' browsers. These certificates obtained a digital signature from the trusted signature authority. When you visit a secure website, you'll always see a HTTPS. The S represents secure, which means that they are SSL certified. So your browser checks for this digital signature to confirm that it is communicating with a genuine website. And then we'll also talk about blockchain. So blockchain technology like Bitcoin uses digital signatures to authenticate transactions. When you send Bitcoin, you sign the transaction with your private key. Others can then verify your signature to confirm the transaction's authentication and integrity. Okay, and then so what are some ethical and legal aspects of public keys and how are they used? So we'll talk about these different areas such as the privacy rights. We'll talk about the going dark problem, encryption laws around the world, and some ethical dilemmas in cryptography. So we'll start off by talking about the privacy rights. So for encryption is a crucial thing for protecting privacy in digital communication. However, this can hinder law enforcement and intelligence agencies' ability to prevent and investigate crimes. For instance, encrypted messaging apps like Signal and WhatsApp have been used for criminal activities, which has raised a question about the extent to which privacy should be protected. We talk about encryption backdoors. So some purpose that government should have so some propose that the government should have a backdoor access to encrypted data to aid investigations. But this is very controversial, as it could be misused by the government or exploited by malicious third parties. For an example, in 2026, the FBI asked Apple to build a backdoor into a phone used by a terrorist in one of the bombings, although Apple refused to, citing that the privacy risks to all iPhone users. Then we'll talk about the going dark problem. As more communication becomes encrypted, law enforcement agencies worry that going dark and losing their ability to detect criminal activities. This is a significant issue in discussion around regulations for encryption technology. Then we talk about encryption laws around the world. So encryption laws are very widespread. For instance, in countries like China and Russia, encryption is heavily regulated, and the use of certain types of encryptions require a governmental license. On the other hand, in many Western countries, there are strong legal protections for this use of encryptions for privacy and security. These different laws can propose challenges for global businesses and individuals. So now we'll talk about some practice quiz problems. So for this one, we'll ask the question: why is a public key encryption referred to as uh, asymmetric, and what advantages does this bring to secure communication? So take a moment, think about it. All right. So public key encryptions is referred to asymmetric because it uses a pair of keys, one public key and one private key. There's a mathematical relation, but not identical. This is this naturally eliminates the need for secure initial exchange of a shared secret key, a major challenge in symmetric encryption systems. So for that reason, the answer here is A. All right, let's go on to the next one. So, how does the role of public and private key differ in public key encryptions, and what security guarantees does this offer? So, in public key encryption systems, the public key is used for encrypting messages or verifying signatures and is publicly available. The private key, which is kept secret by the owner, is used for decrypting messages or creating digital signatures. This means that even if the public key is used by anyone to encrypt messages, only the holder of the paired private key can encrypt and read the message, providing a key security guaranteed. So with that, the answer here will be B. All right, let's go on to the next one. In the creation of the digital signature, what is the first step? So the correct answer here, well, actually take a moment, think about it. The correct answer here is B. The original message is converted into a hash using a cryptographic hash function. The first step is creating a digital signature. The first step in creating a digital signature is to take the original message and convert it into a hash. This is done by using a cryptographic hash function. As mentioned before, this results to hash as a fixed size and is a unique to each unique message. Even a small change in the original message will produce a significant different hash. So the answer for this one is B again. Okay, so if a hash obtained from decrypting the digital signature matches the newly computed hash, what does it indicate? Take a moment and think about it. So the answer for this one is actually C. The correct answer is C. So the message was not altered during transmission and is from the claimed sender. If a hash obtained from decrypting the digital signature matches the newly computed hash, this means that the integrity of the message is preserved, which means that the message was not altered during the transmission and that the message is authenticated, which means that the message is indeed from the claimed sender. And this is the primary function of a digital signature in the digital communication world. Okay, and then I think we have one more quiz problem for this section is what is the main concern associated with the idea of encrypting backdoors? So, as we talked about earlier, one of the more main focuses here is that um, creating a backdoor can weaken security and expose malicious malicious actors. So the answer here is A. And the reason for this is that the encryption backdoor refers to a deliberately creating a vulnerability or a weakness introducing into the encryption system to allow authorized access by agencies or governments. The main concern is that these backdoors can weaken the security of the systems, making it more vulnerable to exploration by malicious actors. Critics argue that such a backdoor can create a significant risk as they can be discovered and exploited by cyber criminals or state-sponsored attackers. Okay, so next we're going to be talking about quantum computing, adding public key encryption. Okay, so when we talk about quantum computing, we'll talk about it with the public key encryption. So, quantum computing, what is that? So, quantum computing is a rapidly advanced field of technology that leverages the principle from quantum mechanics. It utilizes quantum bits or qubits, which is unlike classical bits, and can exist in multiple states at once during a property due to the property called the superposition. Additionally, qubits can be entangled, meaning that the state of one qubit can directly influence the state of another, no matter the distance between them. So, what are some potential impacts on public key encryptions? The unique properties of quantum computing pose significant threats to the current public key encryption system. Public key encryption includes RSAs and ECCs, heavily relies on the difficulties of certain mathematical problems. Factoring in large components and comprise integers and solving discrete logarithms, respectively. Classic computers cannot solve these problems effectively, but quantum computers has the potential to interrupt this. So what we're going to be talking about next is what is called Shlore's law algorithm. This potentially this potentially disrupts is not just theoretical. Well, sorry, this potential disruption is not just theoretical. A quantum algorithm known as the Shlore's algorithm, if run on a significantly powerful quantum computer, could factor large numbers and solve distinct logarithms exponentially faster than the known algorithms on classical computers. This would effectively break RSA encryptions and ECCs, rendering these cryptographic systems insecure. So the threat of quantum computing is not immediate, as building a quantum computer powerful enough to run these kind of algorithms is considered challenging. However, it is a long-term concern for security of public key encryption systems and is driving the development of new quantum resistance algorithms. All right. So then we'll talk about different things. So we'll talk about the quantum computing potential impacts of quantum. Well, actually, we just talked about this. Oh, let's talk about some examples of this. So, for quantum computing, what are some examples? So, the simple example of a quantum computation could be a quantum bit, as we talked about, is qubit. While a classic bit holds a single binary value of either a 0 or a 1. A qubit can hold both at the same time due to the property called superposition. When measured, however, it collapsed to either 0 or 1. So, what are some examples of some potential threats on public key encryptions? So the impact of quantum computing on public key encryptions can be understood with an example of the RSA encryption. In RSA, the difficulty of factoring a large prime number provides a security base. Let's consider an RSA system using a 2048-bit key. It could potentially take a classic computer more time than the age of the universe to crack this by using brute force. And as we mentioned before in earlier chapters, brute force is trying every single possible option there is. However, a powerful quantum computing using the algorithms could theoretically do it in a reasonable amount of time. So then we'll talk about the Shor's algorithm. A simple example of the Shor's algorithm could be factoring small numbers like 15. So the algorithm would identify a number a, let's say 2, which is less than the co-prime to 15. The algorithm finds the period of the function 2 to the x mod 15, which turns out to be 4. Utilizing this period, the algorithm calculates the factor of 15, which are 3 and 5. While this is very trivial for a classic computer, the same method can be used on a quantum computer to factor extremely large numbers effectively, efficiently, and something not feasible with a classical computer. So then we talk about what happens in the world of post-quantum cryptography. So we talk about post-quantum cryptography is the reference to cryptographic algorithms, usually public key algorithms, that are thought to be secure against attacks by quantum computers. So now we're already thinking, if there's a quantum computer that is powerful enough to break these encryptions, now we need some sort of we need new measures and new algorithms to help us prevent these things in the future. So that is what is called the post-quantum cryptography. So even though current publicly known experimental quantum computers cannot break any practically used in cryptography algorithms, many cryptographers are designing new algorithms to prepare for times when quantum computers become a threat. Some of these algorithms are the following. So we have the letter-based cryptography, we have the code-based cryptography, multivariant polynumeral cryptography, and we have the hash-based cryptography. And I won't go too much into these, but just understand that these are different methods that they're trying to use in the world of post-quantum computing. So again, we haven't reached this level yet, but we're in some cases may want to just get prepared for when this time does happen. Okay, and here are some examples of post quantum computing ideas that they're proposing, right? So when we talk about delivers based cryptography, we talk about the NTRU encryption system as a practical example, which is actually just in theory as of right now. And what it is that it's one of the finalists in the NIST post quantum computing standardization process and is being considered as an alternative to current public key systems in the future. It's practically appealing because offers a strong level of security while also being relatively effective compared to other post-quantum uh, cryptographic systems. And then we have other different factors here, and then you'll see we'll talk about when we go down to the unbalanced oil and vinegar, the UOV, and rainbow signature schemes are other examples. Um, They also have major drawbacks, since that the key size are significantly larger than those of other signature schemes, making it less desirable for many real world applications. Um, and yeah, and then we have all these different methods that we want to do, and then we just ensure that in the world that we get into next, that in post quantum computing, that we're ready and that we have different ways and different algorithms to help us. Cool. So let's talk about some quiz problems here. So for this question, it tests your understanding of potential impacts of quantum computing on public key encryptions. So remember that the primary security base of systems like RSA is the difficulty of factoring large prime numbers for classical computers. So the Sloan algorithm, if run on a significantly powerful quantum computer, could factor these large numbers effectively and efficiently breaking the RSA in similar sizes. So for this one, the quantum computers could potentially use Sloan's algorithm to factor large prime numbers, and that is. Let me grab out my pen. That would actually be number. This would be letter B. Perfect. Next, we'll talk about some more cryptographic methods. So, which cryptographic method involves the use of error correcting code and has resistance all cryptanalysis attacks including those using quantum computers since the inception of 1978. Um, and the answer for this one is so this question assesses the student's understanding of the variable post-quantum cryptographic methods. The correct answer for this one will actually be B, code-based cryptography. So when we look at questions like these on the quizzes, I know I didn't personally run over it, but they were presented here on the slide. So questions like these, when it comes up on the quiz, will then have different maybe wording, right? So make sure that when you look at these kind of questions on the quizzes, that you read the questions very thoroughly, because I'll have similar questions, but wording one might be different. So make sure to keep an eye out for that. All right, let's get on to the next one. So, which of the following statements is true regarding the unbalanced oil and vinegar (UOV) and the rainbow signature schema? So, this question is actually tests your knowledge of the multivariate polynomial cryptography. So, the correct answer reveals that the key classic characteristics of these schemes, they are computationally effective, but has major drawbacks in the size and the large key sizes, which makes them less desirable for real world application. So for this one, the answer for this one is C. All right. Next, we're going to be talking about Bitcoin and cryptography.